I'm going to talk about absolute value functions and their graphs. Just as the absolute value of a number, the absolute value of x, is the distance away from 0, the absolute value of f of x gives the distance from the line y equals 0, or in other words, the x-axis, for each value of that f of x. The graph of the absolute value of a linear function in two variables is v-shaped and symmetric about a vertical line called an axis of symmetry. So when you graph absolute value functions, you'll end up with a v-shaped graph either opening up or down, and there'll be a line of symmetry, a vertical line that goes right through the middle of that v-shaped graph. That's called the axis of symmetry. The graph has either a single maximum point or a single minimum point called the vertex. So the v-shaped graph will come together, there'll be a vertex such as this, there'll be a single minimum point, a low point, or a maximum point, a high point, and that is called the vertex. One way to graph an absolute value equation is to make a table of values. The first step in making the table of values is to determine the x-coordinate of the vertex. The x-coordinate of the vertex is the value of the variable that makes that expression inside the absolute value sign equal to 0. That will be the x-coordinate of the vertex. Then you make a table of values. So once you get that x-coordinate of the vertex, you want to pick a point to the left or a value to the left of that x-coordinate of the vertex and a value to the right of that x-coordinate of the vertex. Because to make a v-shaped graph, you just need the vertex and then you need a point to the left and a point to the right. So choosing x values to the left and right of the x-coordinate of the vertex, substitute those x values into the equation as you would all the other x values, and then you produce your y values, making your table of values. Plot the points and draw the v-shaped graph. So for this y equals the absolute value of x plus 2 minus 4, the first thing we want to do is determine the x-coordinate of the vertex. That's the value of x that makes that inside the absolute value sign equal to 0, which in this case would be negative 2, because if you put a negative 2 in for x, that would make that inside the absolute value sign 0. So that is the x-coordinate of the vertex. When you put negative 2 in for x, get the absolute value of 0 minus 4, and that is just going to be negative 4. So pick a point to the left, point to the right. So value to the left of negative 2 would be negative 3. Value to the right of negative 2 would be negative 1. Keep it close so your graph isn't spread out. So once again, if you put negative 2 in for x, you're going to get an x value, or a y value of negative 4. If you put negative 3 in for x, be the absolute value of negative 3 plus 2. That's the absolute value of negative 1, which would be 1, minus 4, that is negative 3. And finally, if you put negative 1 in for x, be the absolute value of negative 1 plus 2. It's going to be the absolute value of 1 minus 4, and that is negative 3. So there you have your 3 points. The vertex is negative 2, negative 4. A point to the left would be negative 3, negative 3. Go to left 3 and down 3. And then a point to the right would be negative 1, negative 3. Go to left 1 and down 3. Those are the 3 points that make up that v-shaped graph, and that is the graph of y equals the absolute value of x plus 2 minus 4. Another way, and probably an easier way to graph absolute value equations, is to transform the parent function. The parent function is y equals the absolute value of x. Now there are 3 key points that go with the parent function. 0, 0, the origin. You have the point 1, 1, and the point negative 1, 1. Those are the 3 parent function points for an absolute value equation. So imagine taking those 3 points. Let's say you wanted to shift those 3 points up or down. So if you want to make a vertical translation, you can shift those 3 points up. 0, 0, 1, 1, negative 1, 1. You can shift them up or down if you wanted to move that particular graph up or down according to this. If you add to the value of y, remember the transformations that we had, if you add to the value of y, it's going to shift the graph up. If you subtract from the value of y, it's going to shift the graph down. Then we talked about left and right transformations. When you subtract from the value of x, it's going to shift the graph to the right. When you add to the value of x, it's going to shift the graph to the left. So you can take those 3 parent function points, and let's say it was y equals the absolute value of x minus 3. That's going to shift the graph to the right 3. So you can take those 3 parent function points, 0, 0, 1, 1, and negative 1, 1, shift each of those to the right 3, and that would be the graph of y equals the absolute value of x minus 3. Vertical stretches and compressions, we've talked about those. If you want to stretch the graph away from the x-axis, you're multiplying the y value by a number greater than 1. If you want to compress the graph toward the x-axis, you would multiply the y value by a number between 0 and 1. So let's say you had y equals 4 times the absolute value of x. Take those three parent function points, 0, 0, 1, 1, negative 1, 1, and you would multiply each y coordinate by 4, and that would stretch the graph away from the x-axis by a factor of 4. We also talked about reflections. If you want to reflect in the x-axis, or also referred to as over the x-axis, you would take the negative of the value of y. So you'd take the negative of that whole right side, and that would reflect the graph over the x-axis. So for these 3 points, 0, 0, 1, 1, negative 1, 1, if you took the negative of the value of y, that's going to reflect the graph over the x-axis. If you wanted to reflect the graph over the y-axis, which with this, it wouldn't go anywhere because it's just going to be the same thing, but you take the negative of the value of x. So those three parent function points, 0, 0, 1, 1, negative 1, 1, like I said, it's not going to go anywhere, but that would be a reflection over the y-axis if you took the negative of each of those x values. So you can take an absolute value equation and you can graph a new absolute value equation by transforming those parent function points in this case. We're going to graph each equation by transforming the parent function y equals the absolute value of x. So we're going to take that parent function, we're going to move it accordingly to this new equation, y equals the absolute value of x minus 3. So you can see we're subtracting 3 from the value of y. The value of y is that whole right side. The absolute value of x is the value of y. So if we subtract 3 from the value of y, we're going to take those three parent function points, 0, 0, 1, 1, and negative 1, 1, and subtract 3 from each y value. So the point that was 0, 0 is now going to become 0, negative 3. And the point that was 1, 1 now becomes 1, negative 2. And finally, the point that was negative 1, 1 now becomes negative 1, negative 2. So you just simply take each of those three parent function points, shift them down 3 units, subtract 3 from the y value, and that creates the new blue graph. So from red to blue, you can see that graph is shifted down 3 units. We're going to graph y equals the absolute value of x plus 2. Remember, when you add 2 to the value of x, it's going to shift the graph to the left 2 units. So we're going to take each of those three parent function points, 0, 0, 1, 1, and negative 1, 1, and going to shift each of those to the left 2 units. So the point that was 0, 0 now becomes negative 2, 0. The point that was 1, 1, if you shift it to the left 2 units, now becomes negative 1, 1. And the point that was negative 1, 1 now is going to become negative 3, 1. So you have those three new points, taking the parent function points, shifting them each to the left 2 units. That creates the new blue graph. So from red to blue, you can see it is shifted to the left 2 units. Again, I'm going to graph each equation by transforming the parent function y equals the absolute value of x. We're going to y equals the absolute value of x plus 6 minus 1. So there are 2 transformations there. You're adding 6 to the value of x. What's that going to do to the graph if you add 6 to the value of x? It's going to shift the graph to the left 6 units. We're also subtracting 1 from the value of y. The value of y is this whole right side. If you subtract 1 from the value of y, take any point, you subtract 1 from the y value, it's going to shift the graph down 1 unit. So those are the 2 transformations. We're going to go to the left 6 and down 1 from this parent function. So those 3 points, the parent function points 0, 0, 1, 1, and negative 1, 1, if you take each of those and shift them to the left 6 and down 1, you're going to end up with the new graph. And it doesn't matter what order you go in. You could go down 1 and then to the left 6, or you could go to the left 6 first and down 1. Either way, you're still going to end up in the same place. So if you take those 3 parent function points and shift them to the left 6 and down 1, or down 1 to the left 6, you're going to end up with those 3 new points, which would be negative 6, negative 1, negative 5, 0, and negative 7, 0. Those are the 3 new points. That's the blue graph. You can see the red graph to the blue graph. It's shifted to the left 6 and down 1. Going from y equals the absolute value of x to y equals the absolute value of x minus 5 plus 4. Once again, 2 transformations. You're subtracting 5 from the value of x. It's going to shift that graph to the right 5 units, and then add 4 to the value of y will then shift the graph up 4 units. So either you can go to the right 5 and up 4, or you could go up 4 into the right 5, either way, it's still going to end up as the same graph. So take those three parent function points, 0, 0, 1, 1, and negative 1, 1. Again, take them to the right 5 and up 4, or you could go up 4 and then to the right 5. Either way, you're going to end up at the same spot, and that's going to create that new blue graph. That is the graph of y equals the absolute value of x minus 5 plus 4. Take those 3 points, 0, 0, 1, 1, negative 1, 1. Go to the right 5 and up 4. You can see that blue graph is the red graph shifted to the right 5 and up 4, or you could think of it as up 4 and then to the right 5. Either way, it's the same graph. Which is the following is the graph of y equals the absolute value of x plus 2 plus 3. So think about how the parent function was moved to get this equation. You added 2 to the value of x, it's going to shift the graph to the left 2 units. And you added 3 to the value of y, it's going to shift the graph up 3 units. So think about that parent function right there at the origin, 0, 0, 1, 1, negative 1, 1. Those 3 points, if you take each of those to the left 2 and up 3, you're going to get this new graph. Well, it appears this graph from the parent function was shifted to the left and down. Remember, we need to the left and up. This point, it appears, was shifted to the right and down. This one over here looks like it was shifted to the right and up. Remember, we want to go to the left 2 and up 3. So the graph that is the graph when you take the parent function and you shift it to the left 2 and up 3 units, you're going to end up at this new graph. You want to focus on one point, just think about that point 0, 0, which is the vertex. If you take the vertex 0, 0 to the left 2 and up 3, you're going to end up at that point negative 2, 3. So the correct answer here is letter C. That is the graph. When you take the parent function and shift it to the left 2 and up 3, you're going to end up with that graph, letter C. Now, just to revisit this last one, so we know the equation for this graph is y equals the absolute value of x plus 2 plus 3. What about these others? What do you think the equations are on those? Well, this graph, like I said, it appears it is shifted to the left and down. So if you go to the left 2 units and down 3, to the left 2 and down 3, the equation for that, you'd be adding to the value of x, but subtracting from the value of y. That would be y equals the absolute value of x plus 2 minus 3. How about letter B? It appears that parent function was shifted to the right 2 and down 3. Well, if you went to the right 2, it would be the absolute value of x minus 2, and then down 3, you'd be subtracting 3 from the value of y. So the equation for that one would be y equals the absolute value of x minus 2 minus 3. And for this one here, it appears the parent function is shifted to the right 2 and up 3. So if you took it to the right 2, it'd be y equals the absolute value of x minus 2, and then up 3 would be plus 3. So y equals the absolute value of x minus 2 plus 3. Those are the other equations for each of those graphs. We're going to graph y equals 3 times the absolute value of x. We're going to do this 2 different ways. The first way we're going to do it to talk about it is transforming the parent function. So when you multiply the y value by 3, that's stretching the graph away from the x-axis by a factor of 3. So take those 3 parent function points, 0, 0, 1, 1, and negative 1, 1, multiply each y value by 3. If you did that, the point 0, 0 wouldn't go anywhere. That'd stay as 0, 0. But the point 1, 1, that would become 1, 3. And the point negative 1, 1, that would become negative 1, 3, multiplying each y value of the parent function by 3. Here's another way to look at it. Y equals 3 times the absolute value of x. The vertex is going to be at 0, 0. And then that 3 that's out in front, when it's in this form, y equals 3 times the absolute value of x, that 3 out front is what's called the slope of the right branch. So from your point 0, 0, the slope of the right side or right branch, go up 3 into the right 1 because the slope is 3. And then the slope of the left branch would be negative 3. So from on the left side, from 0, 0, go up 3 into the left 1, and then you would have your 3 points that way. So either way, whether you transform the parent function by multiplying the y value by 3, or whether you put your vertex down and then think of that 3 as the slope of the right branch, the slope of the left branch would be negative 3, you're going to get your 3 new points for that blue graph, and you can see that blue graph is stretched away from the x-axis by a factor of 3. Now if we have y equals 1/2 times the absolute value of x, once again, you could do this 2 ways. You could take the 3 parent function points, 0, 0, 1, 1, and negative 1, 1, multiply each y value by 1/2.
you would end up with staying at 0, 0. That's not going anywhere when you multiply y by 1/2. But this 1, 1 would become 1, 1/2. And this negative 1, 1 would become negative 1, 1/2. So you can see each y value is multiplied by 1/2. You're compressing that toward the x-axis. So that is a compression and that is a stretch. And you can see the difference in the graphs. Another way to do this is, since this is 1/2 times the absolute value of x, the vertex is just going to be at 0, 0, as you can see there. And then the 1/2, that is the slope of the right branch. So from that 0, 0, go up 1 and to the right 2, put a point. And from 0, 0, go up 1 to the left 2, because the slope of the left branch would be negative 1/2. So put your vertex down at 0, 0. Slope of the right branch is 1/2. Slope of the left branch is negative 1/2. You'd have your 3 points that you could draw your V-shaped graph through. So there's a couple ways to do it. Whether you transform the parent function, or whether you think of that 1/2 and that 3 as the slope of the right branch, and then the slope of the left branch would be the negative of those. Either way, you're going to end up with the same graph. And you can see the compression versus the stretch taking place here. When you multiply the y value by 1/2, it's going to compress the graph toward the x-axis. And when you multiply the y value by 3, it's going to stretch the graph away from the x-axis.